So we've accumulated quite a lot of complexity, right? So we started from the Heisenberg algebra with complicated reasoning. We figured out stuff about some R matrix and then something about a product that was derived, that was not guessed, okay? And then we figured that both are Gaussians, so they can be described by quadratics, and quadratics are described by matrices. And we wrote general rules how to compose quadratics according to our funny composition laws, and that amounted to lots of matrix operations. And we mostly proved it. So we proved it. We proved these rules, first of all, intuitively, and then, like we did the second pass with PDEs, which again, you wouldn't expect to see such things in knot theory, but well, you do. And that the PDE thing we nearly completed, but didn't quite, and I don't feel that completing it would benefit anybody. It's just the principle is already clear. And then there are, and then we could go through more details, but only really more details. And also we will be forced to do it anyway later on in a slightly different context. So I'm dropping this, but I wanted to emphasize something. At the end of the day, I mean, the process was extremely complicated, but at the end of the day, everything we do is about extremely simple operations with matrices. Okay? So we should be able to unwrap everything, remove all the packaging, and be left with something really, really, really simple about 2n by 2n matrices. Why 2n by 2n? Because if you have a tangle with n components, then it corresponds to the Heisenberg algebra tensor to the n. So it covers, so it's invariant. We leave, I mean, after you normal order, after you use the ordering map, the invariant will be living in things of the form omega times e to the q. And q is a quadratic in the variables xi and pi. So for each component there is one x and one p. So overall you have quadratics in 2n variables, and a quadratic in 2n variables is just a 2n by 2n matrix. So really Q belongs to matrices of size 2n by 2n, and omega is just a scalar. Well, speaking of scalars, what are the coefficients? So we started with with t, a lowercase t, but then we found that only uppercase t appears in the formulas. So, sorry, that only the exponential of lowercase t appears in the formulas. So we call that exponential uppercase t, but it can appear with power plus or minus 1. And then all the operations, and you're welcome to check this. I mean, this is happening over the rationals because exponentiation involves dividing by n factorial. But the composition laws that we ended up writing, all these 1 minus f times g inverse, were all written over the integers. So, so in fact, so in fact, all that you will ever get are rational functions with coefficients integers in the variable t. So this is in, so all of these things are with coefficients in some ring, where the ring is rational functions in the variable uppercase t. Okay. So then there is a meta theorem. So if we have an invariant valued in R cross matrices of size 2n by 2n over polynomials, and it's defined by, at the end of the day, matrix operations, we should be able to unwrap all the remove all the complexity and turn it into matrix operations, elementary ones, that even that any A-level undergrad taking linear algebra should be able to understand. Right, so I'm saying it is still complicated because we use the very, very long procedure. But since at the end it's very simple, at the end it's just matrix operations, we should be able to write it directly as matrix operations. So that's what I want to do today, to make it much, much, much simpler. Okay. Except I missed the point to our benefit. So all of these quadratics, both of these quadratics, are what I will call balanced. So what does balanced means? It means, well, if you're talking about Latin letters, it means equal numbers of p's and x's in every term. Okay, so basically no xx terms and no pp terms. Okay, so equal number of x's as p's. This is if you're talking only about Latin. But you see, if you're also allow Greek letters, then you sometimes get p and pi. So p and pi are sort of opposite. So if I count the pi's with the x's, then so in other words, if I weight x's and pi's with positive weight and p's with negative weight, then the terms are still all balanced. But likewise here, so xi should be of opposite x and opposite weights than x. So xi should be weighed with the p's. So if I again take each of these with weight +1 and each of these with weight -1, then up to here everything is balanced. But then xi and pi also have opposite weight, so everything is balanced. Now, when you compose, how do you compose? The composition operation acted by, was applying the differential operator, the infinite order differential operator, what was it? Basically basically contraction, okay, contraction, but each contraction killed one variable and its dual. But the variables and their duals have opposite weights, so contractions keep the balance. So the conclusion is that everything stays balanced. So the things we start from are balanced, compositions preserve balance, so everything will always be balanced. So in fact, Q here is a balanced quadratic. But what's a balanced quadratic? So it's a quadratic that cannot have pp terms or xx terms. So it only has px terms. So you can write it as sum ai j pi xj. But now it's a summation from 1 to n. Right? So in fact we get meta theorem number 2, which says that there exists an invariant with values in R cross matrices of size n by n, not 2n by 2n, and then even B-level linear algebra students should be able to understand it, if we only are able to write exactly what it is. Okay? So let's try to write it exactly. So first, to fully understand it. So first of all, again, if the invariant is valued in scalars cross matrices, here is a nice way of writing the invariant. So we write the scalar up here, and then along the rows of a matrix, we enumerate the p variables, p1, p2, and so on. Along the columns, we enumerate the x variables. And then as the entries we put here as a matrix, aij. So basically, the invariant is a matrix and a scalar, and then just the labels fit nicely in the picture. Okay? So for example, Rij plus minus 1 will be the following. So so the labels are pi, pj, xi, xj. The coefficient is 1, the prefactor is 1. So this is 1. And the terms of the quadratics are, well, pi xj with coefficient t to the plus or minus 1, minus 1. So pi xj, so this is t to the plus minus 1 minus 1. This is 1 minus t to the plus minus 1. This is 0 and this is 0. Okay? Similarly, eta I is even simpler and comes out to be 1, 0 pi xj. And I'm not telling you how I will denote mijk, because I see mijk, I de-objectify mijk. Sorry. So mijk started its life as an operation. Then I've objectified it. I turned it into an object. And now I'm de-objectifying it. I'm thinking of it back again as an operation, so I don't need to write it. I need to tell you how it acts on things like that. Okay, but I do need to tell you one more thing. Remember that I could also multiply things. So if you multiply two things, so if you multiply omega e to the q1 with omega 1 with omega 2 e to the q2, the result is omega 1, omega 2 e to the q1 plus q2. So the conclusion is that if you have two tangles, so ki, and the invariant of ki, so I goes from 1 to 2, is like omega I ai, and then some labels. And if the set of labels is disjoint, then the invariant of, sorry, the eraser was at the worst possible location. Then the invariant of K1 cross K2 will be, so you multiply, which means multiplying the omegas and adding the quadratics, but adding quadratics on disjoint sets of variables means the block diagonal sum of the corresponding matrices. So the invariant of this will be omega 1, omega 2, a1, a2, 0, 0. Here the labels of k1, here the labels of k2, and likewise down here. Okay. But now comes the hard part. So I want to understand how Mijk acts. So, how does Mijk act on a thing like this? Right, so you have a scalar, a matrix that represents some quadratic form, and I want to see how Mijk acts on it. Okay. I could give you the answer by going through everything we've done so far. And we've done more complicated stuff. But I think I want to do it in a, well, what might end up being a more complicated way, but also more complicated in a technical sense, but simpler in the sense that you can see everything. So here it here it is. First of all, I need a picture for this. So I want to reduce everything to pictures and playing games with pictures. So I need a picture for this. Let me tell you what my picture will be. So actually, it's my usual picture, namely like a coupon with a quadratic and a scalar on it. So I don't know, let's put the scalar here, it's not interesting. Or you know, even let's put it in the most harmless place, I don't know, out of the way. And then it has, so the coupons we had early had a Greek side and a Latin side. But now I'm already looking at the values of the invariant. So all the Greek letters are not there. Only Latin letters. So there are Latin letters here on the right. Only Latin letters on the right. But these Latin letters are divided into two types, the P type and the X type. So here is the division line. I'll put all the X's below and all the P's above. And then, but in fact there are many types of Latin letters. There are PJs, there are PIs. So I'm trying to apply Mijk. So the letters PI and PJ play a special role. And you know, maybe just to avoid confusion, I shouldn't have called it AIJ, I should have called it AMN. Let's use different letters. And then there are the rest. Just all the other P's. Okay? And likewise the X's. So there is things that XI's, there are XJ's, and then there are XS. S and R run over the rest. Okay? And really, this is just the side of the coupon. The information in the coupon is that there are lots of quadratic things, and they all go from the P side to the X side. So let me indicate it by saying that there are lots of things like that, and each come with a coefficient AMN. So there is an AII, AJI, AIJ, PRS, all of those appear here. Okay. Now, I want to compose it with the coupon for, oh yeah, I erased it, unfortunately. With the coupon for multiplication. So maybe I'll rewrite, no, I will not rewrite it, I'll just write the coupon for it. But what is the coupon for multiplication? So it does have okay, it also has a dividing line here, and also a dividing line here. So here will be the pi's, here will be the xi's, here will be the p's, here, sorry, the p's, here will be the x's. So here there is a peak, like a place for the pk, and a place for all the other p's. Here there is a place for xk, and a place for all the other x's. And for the inputs, I have psi j, pi j, pi I, and all the other pi's. And for the inputs here, I have psi I, psi j, and all the other psi's. And what's the content of the coupon? So, okay, so maybe I should have written. So the content was pi I plus pi j pk plus psi I plus psi j xk minus psi I pi j. So, so let me draw it. So I have pi I and pk, and I have pi j and pk. I have psi I and xk. I have psi j and xk. And I also have a psi I pi j. And actually, let me adopt the convention that these lines, I indicate these lines as arrows going from the weight 1 to the weight -1 variables. So here I wrote it as an arrow, and if I wanted to write the same here, I'll have arrows going this way. Okay? And in fact, when I multiply mijk, when I apply mijk to something, I keep all the other variables. So there are also arrows going this way and arrows going that way, which do nothing, just identities. Okay. Now, what does composition do? Composition means connect an arrow head from this side to an arrow tail from that side, or an arrow head from here to an arrow tail from here. So now I want to compute the output, and in the output I will only be starting from the right-hand side and exiting to the, there are no Greek letters. So everything only connects to the right-hand side. So, and I'll have pk, pr, xk, xs, and I will obtain the output by contracting things from here with things from here. And again, everything are exponential reservoirs. So I just, you know, if I contract something, I use it, but it stays. I have more copies if I need. So basically, what I need is to count paths going from, like, you know, if I want to know what is the component of pk, I should be counting, or sorry, what is in the output, what is the coefficient of pk xk? I should be counting all the passes that start from pk, go through here, come back, go through here, come back, and end up with xk. Okay? Oh, and I made a mistake. I forgot to say, this thing here comes with coefficient -1. This thing here comes with coefficient -1. And for debugging purposes, you'll see in a moment what I mean by debugging purposes. I'll give it a name, and the name will be Bij. So Bij is a fancy name for -1. Okay? Good. So let's start computing. So what is the weight of PR goes to XS? You know, suppose I wanted to start here and end here. How could I do that? In other words, in the output, if I write the output as, you know, if I think of it as a matrix CMN, then I'm trying to compute CRS, where R is an arbitrary input, not one of I, J, and K, and S is an arbitrary label, not one of I, J, and K. Okay, so what is this? So, if I start with PR, how can I get to XS? So, I have to go to pi R, then it gets glued to PR again, and then there are two possibilities. I can either go directly to XS, and that will give me an ARS, or I can go to, so basically, you know, once I connect to the coupon on the right, I have to go out, unless I connect to it here. And then I loop back. So, or I could go to XI, loop back, connect, go backwards. That will connect me to, well, to pi j, which connects to a pj. And then I could continue to xi, and then continue looping around, and eventually I will have to exit. At some point I will exit. So what will I get? I will get, so first of all, AR. So I need to go from somewhere here to down to xi. So ARI. Then I will be forced to go up here. So that will give me a Bij, a contribution Bij, which is secretly we know that it's -1. Okay? Now I am here. No, I am here. And now I can continue looping an arbitrary number of times. You know, in Unix, when you, or not no, not in Unix, in regular expressions, when you say A star, it means an arbitrary number of A's. So I'll adopt the same notation. So now I can do A, J, I, B, I, J, any number of times. And now you see the point of the debugging of the Bij. Sort of, I always go to, the adjacent letters must be the same. And you can only star something if it starts and ends with the same letter. Because only then you can compose in loops. Okay? So after doing this, I'm still here. So after doing an arbitrary number of loops, I'm still here. And then I just have to exit, and that's in AJS. AJS. You see, I can't make mistakes. Well, maybe I can, but okay. Similarly, you know, I don't think I want to do all the, there are 4 things to check, like generic to generic, K to generic, generic to K, and K to K. I don't want to do all of them. I'll just do the next one, which is the coefficient of C, the coefficient CKK. So this is the paths that start at PK and go to XK, and this is a terrible mess. This is the hardest. So let's do it. Okay, how can I get from K to K? So I have 2 potential stars, right? PK connects both to pi I and to pi j. So I could do this, or I could do that as a first step. So let me keep these colors and separate them, okay? So if I do the red things, then I'm at pi I, so now I'm at pi, and I want to, okay, what can I do? I'm at pi, I can go straight out to AJ, and then output from here. So I'll get, the contribution will be AIJ. Or I could go, so instead of going to J, I could go to I. So to go to I, the contribution will be AII. But after I've gone to I, I can do I can either exit directly, which will give me a 1, or, so now so if I didn't exit directly, it means that I took a Bij. So I could take a Bij. But if I took a Bij, I am now here, which connects to here, to Pj. And now I'm ready to do an arbitrary number of loops. So, so the next term is the same thing as here, Aj, Bij star. And then, well, I've done my loops, I'm here, and I want to exit. But there are still 2 ways to exit. I can either go to Xi and then go out, or go to Xj and then go out. So I get 2 contributions. Aj plus Ajj. And both of them are connected to the outside. Okay, oh, sorry, I blundered. I was hoping, I wanted to do, so these are the red options. And now let's do the green options. So, I could start at Pk, and then go to pi j, which connects to a Pj. But I've been here already. So I can just continue from here. No, sorry, from here. So plus AJIBIJ star followed by AJI plus AJJ. I hope I'm not messing up. No, I'm not messing up. Okay. This is still not stuff that a B-level linear algebra student will understand. This is still quite intuitive. So I want to make it even simpler. Okay, well, this isn't simple. Sorry. I want to make it simpler, not even simpler. Okay? So, okay. So let me change my notation back again to matrices. Okay? So I have this matrix, and I want to apply Mijk to it. So in this matrix, clearly rows and column I and j are singled out, are behave differently. So I write it as omega times omega, and then here is the row of I, here is the row of j, and here are all the rest. And likewise, here is the row of I, the column of j, and all the rest. And now let me give specific names to the entries of this matrix. So the names I like are alpha, beta, gamma, delta. You probably can guess why. And then, I mean, the name here, what stands here is really a whole row of entries. So I indicate that it's a row by having a vertical line in the middle of my letter. So this is theta and this is epsilon. And here there is a whole column of further entries. So this is phi and this is psi. And here, this is all the rest of the p's and all the rest of the x's. So this is really a block matrix. So a block. So it's the Greek letter uppercase psi. Okay? And now I need to tell you where it goes. Okay? So it will go to something of the form a scalar here, a coefficient for xk and pk here, and then all the rest of the x's and all the rest of the p's down here. Okay? But now we have to figure out, for example, what appears here. Okay? So we have to figure out what appears in each of the boxes. So what appears here are the CRS's. So all I have to do is to write the CRS's using the new notation. So ARS is just an entry of psi. So it's really psi sub RS, if you wish. Okay? To this I want to add ARI. What's ARI? It's going from R to I, so it's an element of phi. So it's really phi R. After this, I want to do AJI, sorry, BIJ, so that BIJ is just a minus sign, so this plus became a minus. And then I do an AJI BIJ. AJI is gamma, and Bij is -1, so negative gamma star. But what does star mean algebraically? So in general, give me a Greek letter I haven't used yet, mu. So what does mu star mean? Mu star means sum of mu to the, give me a letter I haven't used. I don't know what, mu to the L. L goes from 0 to infinity, so you do mu L times. But that's just 1 over 1 minus mu. So minus gamma star is really 1 over 1 plus gamma. So this is 1 over 1 plus gamma. And then AJS, JS, so epsilon S. I hope I'm not messing up. Yeah, epsilon S. Okay? But this means that what I have to write here is just the matrix whose entries are, which is built of two parts. One part is the original matrix psi, And from this I subtract, but you see this is the product of the column vector with a row vector. If you multiply a column vector with a row vector, you get a matrix of the same dimension as you wanted. So this is minus phi times epsilon divided by 1 over gamma. 1 divided by 1 plus gamma. And this makes sense, right? This is a matrix, this is a vector, this is a column vector, this is a row vector. Again, you can tell by the way they're, and it's the right size, it's the right thing. Okay, so now I need to do the same here. And this is a disastrous mess. But again, everything is straightforward. So Aij is ij, it's beta, plus Aii is alpha times 1 plus Bij, oh, Bij is negative 1, sorry, so this is just negative 1, times Aij star is as before 1 over 1 plus gamma, times Aj plus Ajj is gamma plus delta. Aj, it's gamma plus delta, multiplying gamma plus delta. That ends the first line, and now comes the second line, and the second line is again 1 over 1 plus gamma times gamma plus delta. And then comes a simplification that anybody can do on their spare time. Yeah, I didn't make any mistake. This is 1 plus beta times minus 1 minus alpha, 1 minus beta, no, 1 minus delta, divided by 1 plus gamma. Again, that's just brainless simplification. This is high school, not even linear. So the thing that appears here is 1 plus beta minus 1 minus alpha, 1 minus delta, divided by 1 plus gamma. And finally, so I didn't do it, but I could have done the remaining two boxes in the same way. I'll just tell you what comes out. I'll just tell you what comes out. What comes out is theta plus 1 minus alpha epsilon divided by 1 plus gamma, and psi plus 1 minus delta phi divided by 1 plus gamma. And notice that all dimensions make sense. So you see, this was supposed to be a long row, and indeed it's a row plus a scalar times a row. This is supposed to be a column, and indeed it's a column plus a scalar times a column. So everything fits. Okay. Now you look at it a little more. You look at it a little more, and you realize that 1 minus alpha, or alpha never occurs free. It's always 1 minus alpha. And likewise, delta never occurs free. It's always 1 minus delta. So basically, C's always come with 1 minus. Okay? And the off-diagonal things appear free. So it makes sense to switch to the matrix 1 minus this matrix. Okay? So in other words, let me define gamma of omega in the matrix A to be omega times times e to the quadratic defined by 1 minus the matrix A, instead of the matrix A itself. Okay? And leave space for some fudge factors that, here. I'll fix the omega. I didn't deal with the omega part yet. And then on such gammas, there is also an operation Mijk, right? And it's the same. I mean, it's just all you have to do is to conjugate this operation with replacing a matrix by 1 minus the matrix. So it's also an operation of the form omega alpha beta epsilon gamma delta theta. No, sorry, first theta, then epsilon, and then phi psi bulk goes to some matrix. So let me write what this matrix is. Okay? So this matrix, so here Mijk, in this language Mijk, so again it's a bit of arithmetic. You have to do 1 minus each term, and also in also the diagonal entries replaced by 1 minus what they were, and the off-diagonal entries replaced by their negatives. So I mean, you just it's a bit of calculation, but what comes out is beta plus alpha delta divided by 1 minus gamma, theta plus alpha epsilon divided by 1 minus gamma. Finally, okay, psi plus delta phi divided by 1 minus gamma, and psi plus phi epsilon divided by 1 minus gamma. How much time do I have? About a minute and a half. This is still a bit too hard for a B student. So let me tell you how to view it. So basically, I'm trying to do an Mij operation. So I look in the corner where I and j meet, and then I look at the and then that corner defines gamma, and then that corner defines a column, and a row. So what I do is I remove this row and column from the matrix. So I'm left with beta, theta, psi, and psi. So beta, theta, psi, and psi. And I add to the result the product of the of the column I removed with the row I removed. So I've removed alpha phi, and the row is beta theta. So when I multiply alpha phi with beta theta, delta epsilon, I've removed alpha phi and delta epsilon. So when I multiply this row with, this column with this row, I get exactly the other terms that appear here. So now it's simple enough. So basically what I do is I look at row I and column j, take their product, divide by 1 minus gamma, and add to it the matrix in which you remove, add to it the original matrix and remove the row I and the j column. Okay. So that's what this is. Oh, and I failed to tell you what happens with the scalar. So really the right thing to do is to also invert the scalar, and then what happens to the scalar is that omega becomes omega multiplied by 1 minus gamma. Yeah, and Okay, that's all I have to say. Well, no, that's far from all I have to say. That's all the time I have. I wish I taught, okay, I'll tell you in one word. I mean, implementing it is a complete triviality. Basically, you remove row, remove column, and it's just simple linear algebra. And executing it is super fast because there is just nothing here. So if I had a little more time, I would have given you an estimate on the computation time. I don't have time. But I'll just tell you that this is so easy that you can use it to compute the invariant of nodes with up to 1,000 crossings. And the invariant that comes out to be, we didn't prove anything, but the invariant so far came out to be the Alexander polynomial. So this is in fact the fastest way I know to compute the Alexander polynomial, and it works with nodes with up to 1,000 crossings. So yeah, I'm sorry, well, I said the theorems are easy, but deriving them isn't. So okay.